Hi everybody, and I'm going to try to do something to explain exactly what's special about this particular problem that I sent you. Probably at this point, you might have noticed that the first condition, which we shall call number 1, either J or K must be selected, but J and K cannot both be selected, is a biconditional because it's telling me exactly one of two players, J or K, or one of two people must go. Can't be 2, can't be 0, must be 1. And the second one, number 2, tells us the same thing. Whereas number 3 does not tell us any such thing. Number 3 just says N cannot be selected unless L is selected. And that's testing whether or not you recognize what unless means. And then number 4 does the exact same thing. And for some reason, my pen got fat, probably because I pushed a little harder. I don't know, I'm still getting used to all of this fancy equipment. Anyway, so I'm going to have 4 conditions, but the first 2, number 1, is going to be a biconditional. It says if J is selected, then I also know that K is not selected, because if J goes, K can't, because they can't both go. And that means if K is selected, then that means J can't go. But it's also telling me that one of them has to go. And the right side rule would indicate that neither of them has to go, which is naughty, because the first rule says that one of them must be selected. So that would mean that if J does not go, then K has to go. And that if K does not go, J has to go. And our second condition does the same thing. Our second condition says, if either N or P must be selected. So if N is selected to go to the diplomat dinner, then P cannot go. And if P is selected, then N cannot go. But then it also means that if N is not selected, then P has to go. And if P is not selected, not P, then we know that N is going to be going to the party, dancing with Ramses at the party. Okay, our third condition says N cannot be selected unless L is selected. And unless means what? It means if not. So if not L, then N cannot be selected. So if not L, then we know that N cannot be selected. And that means that if N is selected, then L has to be selected to go. So if N is, excuse me, that doesn't fit there. If N is selected, then L is selected, and that's kind of a wonky N. I'm going to try to fix that. If N goes, L goes. And our fourth condition does the same thing. It says unless means if not. So if not K, then Q cannot be selected. So if no K, then no cucumbers. And so if Q is selected, then K has to go to the party or the dinner or whatever. So far, so good? Gosh, I hope so. Okay, so from there, we can start combining our logic, and we know right away that because we've got a pair of exactly one of 2 biconditionals, that we're going to have a mutual exclusion and an affirmative duty. So J and K count as exactly 1, and N and P count as exactly 1 person. One of them will go and one of them will not go. But we have one additional piece of information that was easy to kind of overlook, and it's logically very, 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 very valuable to us. And it's this. Way up here at the very beginning, it says, we've got a group of 7 people, J, K, L, M, N, P, and Q. It tells us that exactly 4 people are going to be selected. That means 4 of these idiots have to go to the party, and that also means that 3 of them cannot go. So we know 4 go and 3 no go. And to us, that puts a numerical requirement on things. That tells us that there's a limited number of things that we can have. We can have 4 going and 3 not going. And that extra piece of information to us will be super, super useful. And we'll see why in just a minute. So now we get to doing our double ups. And we go, okay, J. Is J an antecedent anywhere else? Niet. Negative K. Is negative K an antecedent? Well, down here, negative K gets us J. But that always happens in a biconditional. Basically, J and K count as 1. So if K doesn't go, J goes, and so negative K will always get us J, which doesn't help us. Do we have any other negative Ks? Yeah. If we got the unless rule right in number 4, we have negative K gets us negative Q. And we go, and no Q. And so now we know that if J goes to the party, 2 of our 3 people who do not go are going to be K and Q. Who does our third person who doesn't go to the party have to be? We'll come back to that in just a minute. Now we go looking for negative K antecedents. Oh yeah, we already did that. And the negative Q is not an antecedent anywhere. So it looks like we're done. But it turns out we actually know more than that. Because if Q doesn't go to the party, that means what? Let's think about this for a minute. We've got J, K, L, M, N, P, and Q who could all go to the party. Now, if J is at the party, if that's something that we know, then we know K and Q aren't at the party. And we also know that N or P has to go to the party. So we can add that on. And here is our first instance where we have on the right side an OR. But we have a special kind of OR. It's an exclusive OR because we've been told not both. Only one of them, and exactly one of them has to go. So N or P, but not both, have to go. So if J goes to the party, K can't, Q can't, and one of N or P has to go. And that's 1, 2, 3, 4, 5 of our 7 people. Well, hang on just a minute. If J is one of the people who goes, and K and Q are 2 of the people who don't go, and one of N or P has to be our third person, then who's left? Think about it for a second. If J goes, and K and Q stay home, they're cleaning out the fireplace with Cinderella or whatever, and either N or P, one of them goes, and then the other one stays home with K and Q. So either K, Q, and N won't go, or K, Q, and P won't go, because one of N and P has to go, but both of them can't. So one of them's going to be home with K and Q. That means M and L from our original list, M and L, both of them would have to go to be the other 2 people who go. So M and L would have to go. Because we have that numerical 4 go, 3 no go rule that was kind of hidden in the very beginning of it, we can use that math advantageously to see, once we know that K and Q are out, we know that the third person who doesn't go has to be one of N or P, and that forces M and L to go to the party. So if N knows that J is going to the party, and N really doesn't like P, N could screw over P by, like, I don't know, faking a sprained earlobe or something, or, you know, say, I gotta wash my cat tonight, and can't go to the party. That would force P to go, and that would also force M and L to go. And for us, that's beautiful because it kind of gives us a double smiley face. We know that J and N and M and L can all go to the party together, and we know that J and P and M and L can all go to the party together, which is kind of nice. And when we move down to the contraposed part of that first rule, if K no J, we go looking down the left-hand side for other Ks, and we don't see any that are worthwhile, right? No Ks, no Ks, no Ks. And then we go looking for negative Js on the antecedent side. Negative J gets us K, and negative J doesn't get us anything else. This contrapositive gets us Jack, gets us nothing at all. I'm going to put an arrow there so we don't confuse it with a minus side. I'll put a little JS here for jack squat. It gets us jack squat. Now we'll notice something else. If K didn't get us anything and negative J didn't get us anything, when we flip it around for the second half of the biconditional, we're just going to have another negative J and K. They've just changed positions, but negative J is still going to get me nothing, and K is still going to get me nothing. In other words, I'm going to have a matched set. These two are going to be the same, and then negative K and J is going to get me the same thing as J and negative K, because they're both going to have the same antecedent effects. So this pair is going to be a matched set as well. And for us, that's useful because that means when we have biconditionals, we only have to do the first two and then know that the second two are going to form a matched set. We just need to be careful to make sure that we pair off, because remember how I said in class, the order that you write these in doesn't matter. But what does matter is that J and negative K here will get me the same thing that negative K and J gets me down here. So I need to make sure I match them off appropriately. Because if you have a question about K not going to the party, if K is not selected to go to the party, then blah, 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 blah. Well, negative K means J, and that means the J rule. So we want to make sure that we attach it to the right rule so that we get the right outcome. But if K doesn't go to the party, we know it's the same thing as J, N, M, and L, or J, P, M, and L. Those are all the things that have to be true with K and Q not going to the party. And we can do the same thing with N, and we can do the same thing with negative L. We can do the same thing with all of our rules, keeping an eye on the 4 that go and the 3 that don't go. So there's a little clue to extract a little bit more from your logic, because most people, and when I say most people, I mean almost everybody, way better than 99%. See where I'm drawing this little arrow right here? This is where they're done. They stop right here. They don't think about these numbers as being important, and they don't use them advantageously to get all the rest of this and see, oh, there's 2 complete options, JNML and JPML. And when J goes to the party, that's the only 2 ways that it can work out, JNML and JPML. And if M or L couldn't go, then there would be an M rule that says, an N rule that says it can't go with M. Or if N and M didn't work out, there'd be an M rule that says that it can't play with N, but there aren't any. The logic is completely consistent. M's not an antecedent, and positive L is not an antecedent. It's only a consequent. And P is an antecedent, and P will just get me the no N, which is exactly what I have in my exclusive OR box anyway, right? So take a few minutes and consider this, and then go back and sort of try to reapply it and see if you can squeeze more out of the other rules. And we'll go through it on Monday and see exactly how useful it is. One other thing that you might find useful, and we'll go over this in more detail on Monday as well, is I knew at the beginning that I had to have 4 people go, 4 people go, and I also knew that I had to have 3 people not go, and I knew that one of my 4, and we'll call this the go side, and we'll call this the no-go side. We knew at the very beginning that J or K, but not both, had to go to the party. So that first spot on the go side had to be J or K, and the first spot on the no-go side had to be K or J. And the same thing with the second spot on the go side. It had to be N or P, and the second person on the no-go side had to be either P or N. Well, if I look at my list up here of players, of the people who could go to the party, J and K, if I just kind of cross them off, and P and N, if I sort of cross them off, just leaves me L, M, and Q way over here. So on this no-go side, there's only one spot left for L or M or Q. And what that means is, if L doesn't go to the party, M and Q have to go. Yeah, if Q doesn't go to the party, L and M have to go, because there's only one spot for these 3 idiots to not go. So they're in a super game of who can force the other 2 to go, because nobody wants to go to this party. If you've ever been to a Diplomats dinner party, they're boring as all hell. It sounds fancy and you get to dress up and play important, but really it's stupid and boring, and they talk about boring stuff, and it's just a waste of time. but you do get good free food. So 2 of those 3 always have to go over to the other side. 2 go over here and 1 goes over here. So anytime that you see, like in our first rule, that Q doesn't go, then you know that M and L have to go. And if you had in a rule like down at rule 3, if L does not go to the party, then N does not go to the party. We also know that if L doesn't go to the party, it goes in this chair right here, the no-go side. That forces M and Q to the other side. Most people won't know that. Most people will miss that. That's way above what I'm supposed to be teaching you, but you guys are kicking some serious butt right now, and I don't feel really bad about going up a level. You might as well get the advanced stuff. What the heck? So you can think about it this way, and this helps you to clarify the numbery thing and see, oh yeah, if I just know one of L, M, and Q loses, I know the other 2 go, and that gives me extra antecedents to work with, right? Like down here in this rule. Number 3, let's go back to that one just for a second. If L loses, then that means M and Q have to win, because L would go here and then M and Q would go over here. That's only if L loses, right? If L loses, then it goes here. But if M loses, then L and Q would have to go over here. But if L loses, like in rule 3, we know that L has lost, therefore we know that N has lost. That would mean that M and Q would have to go to the party, and Q is an antecedent that forces K to go, and K is an antecedent which forces J not to go, and it starts filling itself in real nicely. But most people miss that because they overlook the fact that we've got this numerical requirement that gives us extra logic. So take a stab at that, play with it, work it through, and I'll see you on Monday.